Howdy, I'm Bill Higgins from the Chicago Space Frontier Society. I'm in the allegedly real world. I'm an engineering physicist at Fermilab, which is a big particle accelerator facility. It has nothing at all to do with near-Earth asteroids, but I find it fun to investigate these sorts of things. This is a general track talk, so it's not going to be very technical at all. I think you'll find it. There's a modest amount of science in it, but I'm not going to get really deep. So I hope you'll excuse that if you were expecting something really professional. Instead of saying big fingerprint on this slide. So, I like to give this talk about asteroids that come near the Earth and other objects that come near the Earth, and call it Promise and Peril, because it has two parts. As you heard from Dave Stevenson, if you were in the last hour, there are considerable possibilities that asteroids, or some asteroids, have the stuff that you need, the material that you need to feed a good number of space industries. And they're pretty, if you don't find them in near-Earth asteroids, they're pretty hard to find elsewhere off the Earth. In terms of peril, of course, since these things orbit in our vicinity, they may occasionally come visiting, and if they do that, they sometimes make a hole in the ground with unpleasant consequences for the people and other critters that live on this planet. So I'll talk a little bit about the recent efforts of planetary astronomers and other people to worry about the asteroid hazard. The asteroids and comets are small globs of material, and the planets are big globs of material, and all of them presumably came from the big nebula that collapsed at the beginning of the solar system. Almost all of it, I guess 99.9% of it, into a single object at the center, which was hot enough and big enough to start nuclear fusion, and much of the rest into into 9 large objects, and a handful of smaller ones like became the moons that began to revolve around this central object. Actually, at this time in the beginning, everything was dust. There were some gases and lots of little particles of dust which found each other and became bigger particles of dust. But there was a accretion process, a centralized process that made these things collide with each other. And sometimes they would collide and stick, and that made a bigger object, which eventually might become a planet. Sometimes they collided and broke each other into smaller fragments, and then you had more pieces. But the general trend was to reduce the number of sizable objects in the solar system until most of them were swept up by the planets and the satellites. So that today we're left with only a modest selection of small bodies, and an awful lot of them are concentrated into this region between the orbit of Mars here and the orbit of Jupiter here. This is a snapshot of the known asteroids in the solar system with on a particular day in 1988. And so the Earth's orbit is right here, and Jupiter's orbit, which is about 5 times further from the Sun, is right here, and that gives you an idea of the scale. You can see that although almost all of the asteroids lie in the asteroid belt, this region here, there are a few dots here and there in the inner solar system. A small minority of asteroids which can be found orbiting in paths which carry them near Mars or the Earth or perhaps even Venus now and then. If you thought about the asteroids schematically, a few of them are the size of fair-sized moons or planets like the big ones like Ceres and Pallas and Vesta. I believe this is the Ceres here. But most of them are much smaller, small enough that they haven't really they've got enough self-gravity keep them in a spherical shape, and we expect them to be pretty irregular shapes. And if you look at them through a telescope and measure how much sunlight gets reflected off of them and how it varies as they turn, and it takes some spectroscopy to find out a little bit about what they're made of, you'll find that there's a distribution that tends to make the somewhat lighter colored ones be closer in towards the sun, and as you move away from the sun, more and more of the asteroids you can see become darker colored ones. These appear to be a different chemical composition somewhat, and the chemical composition is going to concern us a lot when we talk about using asteroid resources. These objects, or the small population of them which cross the Earth's orbit, of course, occasionally really do interact with our planet, and usually they're pretty small. When we look up at night, you may see a meteor zipping by. This is a picture from 1910 or 1920 or so. If you look at the orbits of these objects, there are over 5,000 main belt asteroids whose orbits are pretty well known, and probably thousands more that have been spotted once or twice, which are not quite well understood enough to be cataloged. And compared to those 5,000 well-known ones, there are about 200 objects known that have orbits that come in the vicinity, take them in the vicinity of the Earth sometimes. There are 200 known or so, but the best estimate is that there are about 2,000 in total Earth-crossing asteroids, and they fall dynamically into these classes. So this is an estimate of the number of asteroids bigger than a kilometer in size, in diameter, which fall into these different orbital classes. Very few of them are A10 class asteroids, which have an orbit that falls inside the Earth's orbit. And the best estimates are that there are maybe 100 of those in the solar system, but the uncertainties are large. Maybe 140, maybe only 60, right? The Apollo class asteroids are those which cross the Earth's orbit. Sometimes they're further away from the sun than we are. Sometimes they're closer. And there are probably about 700 of those. And the Amora asteroids orbit between Earth and Mars. They have so they're kind of neighbors, but they don't actually come as close to the sun as we do much. And there's probably about 500 of those. I don't want to dwell on those specialized categories, but it gives you some idea of the total estimated numbers that we're going to be talking about for big objects. When you get to, if you want to know about objects that are smaller than a kilometer, then the population goes up as you get smaller and smaller. For say 100-meter asteroids, there are a whole lot more of those. But we can probably detect asteroids in the 100-meter and above class pretty well from Earth-based telescopes. So we could, if we wanted to, and we made a concerted effort, we can get an inventory of these. And I'll talk about that a little more later. Here's, again, a picture of the neighborhood around this building. And the orbit of Mars is here, and the rest of the planets are here. To give you an idea of the scale of the other picture, the Earth-crossing asteroids I was just referring to are plotted here. All of their orbits are plotted. So they are going along these loops, each one on ellipse, with the sun in focus, of course. They certainly don't fill up the inner solar system, but they pass through a lot of the points in the inner solar system. And this is a total of maybe 130 or 150 that were known at the time this plot was made. One reason that these objects are extremely interesting to those of us who want to do space development is that the objects that pass near the Earth can be rather easy to get to. That is, they're less expensive for a spaceship to reach in terms of fuel than most of the planets or other objects in the solar system. The nearest thing we can get to, of course, is the moon. And to go from low Earth orbit into orbit around the moon takes you an energy that corresponds to a change in velocity, delta V, in space engineering jargon, of 3.9 kilometers per second. If you want to go all the way down to the lunar surface, you'll have to stop moving with respect to the lunar surface, of course, one way or the other. And you'll have to change your velocity by 6 kilometers per second. Well, there are a few asteroids known, and there's every reason to believe that there are more ones yet undiscovered, which have a delta V cost that are considerably lower than landing on the moon, and not all that much more than actually going in orbit around the moon. There may even be a couple out there which are cheaper than the moon to get to, but that's just speculation, of course. Here's 1986 ML, the one numbered asteroid. It's not mature enough to have a name yet. 4.3 kilometers per second. And Nereus, which has often been seen in talks at conferences of this kind under its old name, 1982 DB, but Nereus recently got an actual asteroid name, so it's been promoted. 4.5 kilometers per second. If they're accessible to spacecraft, well, you know, it's easy to go there and explore them, relatively speaking, if you have the kind of technology that can send spacecraft to the moon or Mars. But, of course, more important, if you can send your explorers there, you can probably send your mining machinery there, assuming you can figure out how to operate mining machinery on the surface of a body that has almost no gravity, and which is probably covered with loose dust that's going to get picked up every time you move anything on the surface. It's a tough engineering problem, and it's real interesting to take a look at how to do that, which I'm not going to cover this year, but maybe some in the future year. But here's a painting by Bill Hartman of what some folks exploring and asteroids might be facing. This looks like a pretty light-colored one. I think you can sort out the colors and sort out the dark and light nature of the light you get back from asteroids. And what you find are that about half of them are S-type. They have similar spectra. And these, of course, since God has already given us some pieces of asteroids, you run around to meteorite collections and stick pieces of the meteorite in your spectroscope, and you compare these signatures of what the meteorite looks like to what the asteroid looks like. S-type asteroids correspond to stony or stony iron meteorites, which are a pretty large fraction of the meteorites. But about 20% of the objects near the Earth are C-type asteroids, and those are real interesting because they're similar to a kind of meteorite called carbonaceous chondrites. They are harder to find after they've fallen on the Earth because they're not exotic-looking rocks, really, and it's a little tougher to identify them because they're so much like dirt and stuff on Earth. They may contain volatile elements of compounds like water and compounds of carbon and nitrogen and sulfur. And that makes them extremely interesting because those are exactly the sorts of materials which you can't get on the moon and you can't easily get anywhere else in near-Earth space. Furthermore, water and carbon compounds and maybe even nitrogen compounds are the basis for making swell chemical rocket propellants and nuclear rocket propellants. So if you want to have a space-going economy that makes that's doing work of whatever kind, building solar power satellites, having some kind of space factory, doing a lot of exploration of various planets and stuff, it's all going to involve sending rockets here and there in the solar system, and all of those rockets will need to be mostly propellant. And if you want to do it the way we're doing it now, all of that propellant will have to be lifted from the Earth. And we know that's fairly expensive. And we are working to make it cheaper, but it's going to remain fairly expensive, even if it gets 10 times cheaper or 100 times cheaper. It's still a lot of money to put a pound of liquid hydrogen into orbit. As long as it's expensive to take this stuff off the Earth, going to the trouble of getting it from a source that's already in space and doesn't cost very much to move from place to place is an attractive notion. And so near-Earth asteroids may well be the basis of fueling, and I mean that quite literally, any large-scale solar system operations. This, of course, makes no sense. You don't, I'll parenthetically say, that you don't need a fuel factory if you're going to send one planetary probe a year from the Earth to go look at somewhere in the solar system, and you're never going to send any people beyond low Earth orbit. And that's the situation that we've been in for the last 25 years or so. But there are a lot of good reasons, of course, to do a little better than that, and maybe even to operate a lot more rockets on a larger scale and send more machines and more people to more places. And if you didn't think that was true, you probably wouldn't have come to this conference. Well, so we have a task before us. Let's say we have some jobs in mind and we'd like to make propellants from asteroids, or use their material for other goods. I'll probably find some asteroids that are likely candidates. You find them by several methods, pretty much. I'm going to talk about not just finding them, but also investigating them. What are they made of? What is their history? And so forth. The good old-fashioned method is to look at the sky, right? Optically, with an eyeball, essentially. And the traditional way to do this is to use a fairly wide-angle camera and move it so that it moves with the stars and take some pictures, maybe with long exposures. If an asteroid passes in your field of view during that, since it does a little bit of motion and stars are not moving, you'll see a streak on your parent, hopefully. This isn't real good. This is only for very fast-moving asteroids, but the ones that are near the Earth tend to be fairly fast-moving relative to other asteroids, the main belt asteroids, because they're closer. And so this is a good old-fashioned way to do it. The groups led by Eleanor Helene and the other group led by Jean Carolyn Shoemaker have done a lot to discover asteroids in the 1980s and add quite a few, maybe one a month, say, to the catalog of near-Earth asteroids over the last 10 or 15 years. Been quite successful, and these are both projects that use old telescopes and a really modest amount of money to expand our knowledge. The Shoemakers work on, no, they work at Palomar, right? I wanted to talk about another group at the University of Arizona, Tom Garrell's group called Space Watch, which has been struggling for many years to build a special charge-coupled device, CCD camera, all the rage in astronomy these days. And that's especially designed for searching for asteroids and very good at finding near-Earth asteroids. It's in a dome on Kitt Peak. I can't tell you which one, but I really wanted to use my Arizona vacation slide somewhere in this talk. And it was raining, so because it was raining, I was able to get the director to show us around. And I was extremely flattered, but it really is an impressive place because it's like there's a little town, a little village up there on top of this mountain, except every house has a dome with a telescope in it, right? Very strange place. somewhere on top of this mountain, we know not what, in what dome, and it may not even have been built at the time I was there. It's a 36-inch telescope equipped with this gadget that Peril and his friends have been working on. And what they do is their telescope actually sort of stands still, and the stars go past it. But they've got it lighted up so that they clock the CCD cells at the same rate that the stars are going by. So the stars, again, make steady images pretty much in their field of view, and it all gets dumped into a digital computer. And they have clever, tricky algorithms for looking for certain things. They take an exposure for a few minutes, and then they immediately take another exposure of the sky, and later in the evening, a few hours later, they take another exposure of the same piece of sky. So, and then their computer goes through and looks for all these blobs and bright dots, and eliminates the ones that are stars, hopefully, and eliminates the ones which only appear in one picture or the other as noise, and flags the ones which appear in one picture or another as either streaks, which is a nice, easy way to detect them, or dots which have moved just a little in a certain way with a certain light distribution in the pixels, and so forth, and says, hey, this could be an asteroid or a comet discovery. And if the data looks good to the operator, they record that and then do some follow-up looking at that piece of sky later on. And the Space Watch camera has been a very good instrument, and it's taken years to develop, but it's finally been shaken down, and with a rather small crew, they have doubled humanity's rate of finding near-Earth objects. And the last I looked, they were getting about 2 a month. So things are rolling up, and we now know about a couple of hundred of these objects. And they, of course, have to observe them multiple occasions, keep following these things in order to get many observations, make a good prediction of the orbit. The kind of asteroids I'm interested in, as I said, are similar to carbonaceous chondrites, so I've got a picture of one here lying on somebody's carpet. It's black stuff, so you know, one signature that you're looking for is a rather small albedo, with a small amount of light reflected from the sun. It's carbonaceous, and so it has its absorption features. It absorbs sunlight in a slightly different way than other than say a rock or metal material would. And the thing to do if you have a suspect asteroid is to take your spectroscope and try to study its optical, the features of its optical spectrum, and especially its infrared spectrum, which is very good for distinguishing among classes of asteroids and comparing them to meteors. You can't actually make 100% confident identification in many cases between what you see in an asteroid and a particular kind of meteorite. There are ambiguities, and this is kind of hard to disentangle. So it's a tougher piece of science than we might think for certain cases. But people are getting better and better at evaluating this kind of stuff and building instruments that are good for studying it. And a remarkable amount of progress in asteroid types and chemical nature has been made in the last couple of decades. Another thing you can do with asteroids, if you're lucky, and if the asteroid you're interested in happens to be passing pretty close to the Earth, within, say, a few million miles, is that you can bounce radar off it. And to do this, you need a rather major radar instrument. And fortunately, the big radio telescope at Arecibo in Puerto Rico is equipped to do planetary radar measurements. They can look at Mercury or Jupiter or whatever. And those are big planets with big radar cross sections. And hitting an asteroid is tougher. But people have been getting better and better at it. In 1992, I believe in December, the asteroid Untitled made a close pass of the Earth, a couple of million miles, and there was enough warning that the radar people could work to get good shots of it, and they managed to get these synthetic aperture radar kind of scans of its surface. And these are almost as good as the spacecraft pictures of an asteroid down there, although you always want to see more detail. You can see that this is beat up. You can see it has an irregular shape. You can see things like craters on its surface, kind of oval depressions here and there. And you can see that it is peanut shaped. It has two blobs and a narrow part somehow, which indicates that maybe it's two rocks that are touching each other. Peril?
Size on it still?
Size. Offhand, I don't remember. A couple kilometers? It's rather small. And for these opportunities, of course, which are still kind of rare, but will be less rare as people discover more and more near-Earth asteroids, right? The radar measurements can be a really useful way to look at the nature of the asteroid. An obvious thing to do, but a difficult thing to do, is to send a spacecraft to go look at an asteroid. And for near-Earth objects, this has not yet been done. But the Galileo spacecraft sent back our first pictures of an asteroid in 1991. This is a rock called Gaspra. On the right, we see Gaspra probably in more or less natural colors. And on the left, we see a funny, tricky computer analysis color stretch that takes the very slightly red parts on here and makes them much more red, pinkish patches here, and takes the very slightly bluish parts and makes them more blue. So we can see that they were attempting to see if there was any difference in the patches of soil on this asteroid. If I were a real scientist, I would say regolith instead of soil. Okay, but you understand what soil is, and you know I really mean regolith, right? Anyway, this detail is not important, but I don't think they really found out anything very interesting from this study. The point is that we know now the shape of Gaspra and something about the number of craters that cover its surface, and a lot more interesting stuff about a bit of its history. Because it's so irregular and pointy, it's probably not been around in the solar system for more than a short time, maybe a couple 100 million years, rather than billions and billions. It has been probably, almost certainly, a chunk that was knocked off some larger body in an asteroid collision. Asteroid collisions, I talked about collisions happening at the beginning of the solar system much more frequently. In fact, we're still experiencing them as the people on Jupiter are about to find out. The dinosaurs on Jupiter, of course, are in big trouble. Here is a slide which may be meaningless to Torontans, but is very useful when I give this talk in and around Chicago. Here's the Planetarium and the Permit Place and stuff are around here. Downtown is more or less in this area. O'Hare Airport is here. So Gaspra is about 19 kilometers long, of which you can see maybe 12 kilometers lit up in this picture. And this gives you an idea of just how big Gaspra is and how many suburbs it would cover if we would set it down on top of Chicago.
Set it down quickly.
Pardon?
So you set it down quickly every month.
Yes, that's true. Set it down quickly enough. Cardinal Exhibit E, right? As I say, collisions happen fairly frequently, and that's a stupid thing to say. They don't really happen fairly frequently, unless you're a sort of cosmic dynamics person, in which case they do happen frequently. But you have to think in like multi-100 million year time scales. I will probably say a few things which apply to such a large time scale. Another painting by this wonderful astronomer in Arizona, Professor William Hartman, who is not only a top fellow in planetary studies, but a painter, and a pretty good painter, certainly somebody who can give us an idea of what processes that these dry independent thinkers talk about actually look like. Here's an example of extremely violent asteroid collision, which is where the relative velocities are large enough that the energy is able to melt and perhaps vaporize the material of the asteroid, and you get this red hot stuff coming out of the collision. This is how we make more little asteroids. And probably how Gaspra evolved. Here's Gaspra compared in size and shape to a couple of more familiar and rather similar bodies. The moons of Mars, Deimos, and Phobos. All of them are covered with pretty old craters. They've been subject to a fair amount of bombardment and collision by much smaller objects in their history. If they got hit with any bigger objects, of course, they'd probably break into smaller pieces, right? So these may be fragments of some larger parent body. In fact, it's likely true because they are differentiated into, that they have a chemical nature that differs from other bodies. I don't want to get into the theory of that, but this thing here looks like a rock. It looks like a stony meteorite. It's an S-type asteroid. Phobos and Deimos are somewhat darker. Deimos also has this suspicious-looking surface, which isn't quite as irregular. It seems smoother than Phobos, even when it's photographed at the same resolution. So there's something about the surface of Deimos that makes it soft and fuzzy-looking, probably a thicker layer of regolith, or as we call it, soil. We tried to investigate these things, humanity did, in the 80s, but the Martians shot down our spacecraft. The spacecraft visits to near-Earth asteroids have been planned, and Galileo is just picking a couple of asteroids up on the way into both main belt asteroids, Gaspra and Ida. But we would like to look at one of the ones in our neighborhood, and the folks at the Clementine Project and the Department of Defense, the Ballistic Missiles Defense Organization, actually planned to do that. And they orbited the moon for a couple of months this year and did a superb job of scarfing up a whole lot of pictures of the moon in a wide variety of wavelengths and getting a topographic map of the moon. And this is great lunar data because the moon, like near-Earth asteroids, the moon hasn't been studied very well by spacecraft in the recent past. So we all cheered about that, but a couple of weeks ago, Clementine left the moon and started off on its journey, which would eventually take it to an asteroid called Geographos, where Clementine would leave her footprint, which of course is number 9, right? And this story has an unhappy ending. A couple of weeks ago, something went wrong aboard Clementine, and she turned on her attitude control jets and kept on firing them until all of the propellant was gone. So she is spinning right now, and unless Dr. Nozette in the next couple of hours tells us something surprising, Clementine will not go to the asteroid Geographos. But still has done a really fine job on getting data for some talk that I'll probably give some other time, right? on moon and in the 90s and what we learned about it. Meanwhile, back at NASA, the people that are supposed to be exploring the solar system in my country, they have a new set of missions called Discovery Class missions, which are supposed to have a tight cost cap. You will spend no more than $150 million to do whatever science that you intend to do. And they make you swear to this, and they will cancel the project if it slops over $150 million. To keep costs low, you have to get very ingenious. But fortunately, the Applied Physics Laboratory at Johns Hopkins University has hired some very ingenious people, including Dr. Robert Farquhar, who has a mind that is not like other humans when it comes to orbits. If you ever get a chance to meet him or hear him speak, I recommend it, because he's involved with the planning for this spacecraft. they want to make something called near-Earth asteroid rendezvous, keep a very light spacecraft, very small, which has a pretty simple set of instruments, but which will do something very interesting and hasn't yet been attempted. Namely, not only rendezvous with an asteroid, come close to it and slow down with respect to it, but actually go into orbit around it. And they're planning to go to an asteroid called Eros, which visits the Earth with a 1996 launch, I think. Is that right? Okay. Well, in the very near future, they're halfway through building this thing. It will orbit. It's got a camera and it's got an infrared instrument to study the nature of the surface. And it also carries a gamma ray spectrometer, so that if it patiently orbits for long enough, and if the solar wind and other cosmic rays kick up enough radioactivity in the regolith or soil of this asteroid, then we'll learn a lot about the chemical nature of the rock without touching it by looking at the gamma rays that are induced and which come off the surface. It's going to orbit so that its dish always points towards the Earth, and its solar cells usually point pretty much towards the sun. These are fixed and they don't rotate. The spacecraft pods low. There's a box full of electronics and some maneuvering engines underneath. It's a pretty good mission and really quite a lot of science if they can make it work for only $150 million. Other objects that are in the inner solar system sometimes are comets, of course. Here's Halley's Comet, which is not really a neighborly object, but it's a swell-looking comet. Even when you look up close at it, here's a picture from Giotto showing nucleus of Halley's Comet and some areas where jets, geysers of dust are fountaining off the surface. Comets are pretty active characters, as you can tell from all the stuff coming out from the nucleus, and they're a fascinating study. But we like them particularly because they are made of even more than C-type asteroids. They're made of the materials that we would like to have for space industry, mostly water, ice, and carbon compounds and other volatiles with dirt and dust mixed in. The European Space Agency is moving ahead with a very ambitious spacecraft program called Rosetta, and Rosetta would fly to a comet and go into orbit around the comet and look down into all this gas and dust and boiling stuff that made that fuzzy picture you saw from Giotto, and look through the fuzzy picture and try to figure out what the surface of the comet looks like. And then controllers will pick a landing site, and Rosetta will make a landing on this comet and sample it with scientific instruments and make chemical studies of it and measure the environment. What is it like to be on a big piece of ice in the middle of a vacuum with stuff spewing out of it all the time, and some of it dark, some of it light? What happens to the temperatures? What is the pressure of the atmosphere? What is the interaction of this with solar wind and magnetospheric stuff, and so forth. It will be a big help in understanding the nature of comets, but it's a really tough engineering job. Rosetta had an ambition a couple of years ago to actually load up some samples from the comet, drill them out and stick them in a return capsule and fire them back to the Earth. But that has proved to be way too complicated and expensive, and I think that just landing on the comet is plenty ambitious enough. So with any luck, in the late 90s or the early 2000s, the early aughts, I guess, we'll learn something about the nature of comets from the Rosetta mission. Comets probably get tired and give up, finish up, use up all of the volatile material that is available on the surface and gradually settle down and become dark little things that don't have active tails. So that many of the dark asteroids that we see may be former comets, and there may actually be sort of a continuous spectrum between comet and asteroid that's really pretty hard for Earth-based astronomers to perceive. And that's one of the things people learn by studying near asteroid or surfing. Well, do I have time to talk about this? Yeah, I guess so. So I'll go over it really fast. So much for the general problems of space industry and trying to find resources near our home. Now for the scary part, which might offer an interesting justification for increased astronomical activity and increased space activity. Here's the moon in the early solar system, as I said, at a time when there were lots of impacts occurring. Were there ever this many impacts occurring all at once? Well, maybe not, but maybe there were. You know, especially if something was hitting, if all of these used to be part of the same object, and they might all hit the moon simultaneously, right? Well, those kinds of collisions still occasionally occur. Summer of 1972, Jackson Hole, Wyoming, extremely lucky photographer happened to be have his equipment out at a time when a pretty large meteor ripped through the sky. Actually, went through the upper atmosphere of the Earth and made a not even battery made a streak across the sky and left the Earth. It was just a bounce. It wasn't a situation where it actually came down. There's a movie film of this as well, and it's pretty impressive. It doesn't happen all that often, especially for a large object, bright enough to see in the daytime, but it does happen. And when it does, sometimes, if we do have a large object hit the Earth, sometimes it leaves a hole. Yeah.
So do you have an estimate of how large that one was that shipped through?
I have forgotten.
I was just wondering how close we came, like, missing New York or something.
Well, I think it was about 100 meters or so, and at its drop, it was circling several kilotons of explosive force.
Yeah, if it was a sort of 100-meter object, it was real dangerous.
It was about a Hiroshima.
About a Hiroshima or so.
So that would be like justification for regular Congress saying, you know, we've already come this close in this last few years.
Yeah. In fact, a few years ago, there was an AIAA position paper put out that said, you know, this could actually happen. This is dangerous. It's obviously a danger to the American people if it should happen to fall in America. And in fact, it turns out that if a really large asteroid falls anywhere on the planet, it's bad for the American people. And I don't just mean the Coca-Cola company and their bottlers worldwide, but I mean that it can alter the climate and we could all starve. So they got a study. They studied it, wrote a position paper, and got it to various congressional people. And they persuaded some congressmen that this was important enough that they put it in the next year's NASA legislation. It's about maybe 1991 or so. That NASA ought to have a study, convene some scientists to study the problems of detecting asteroids that might be threatening and might impact the Earth and do damage to people on a wide scale. And of course, the problem of doing something about it if you do find such an asteroid, which is kind of delicate because you need to have both the scientific people, those very academic, abstract astronomers who worry about things in the outer solar system, and weapons people come to the same conference and then agree on some things. And this actually didn't work out. But they really did have both of those workshops. And the first one, the Morrison report, is extremely interesting to read. It talks about setting up a system to search for near asteroids. I'll talk about that a little, I think. And the second one has never been released to the public. Because basically the people at the workshop could not agree on what to say, what was reasonable to say about mitigating the danger of asteroids. And I really don't have time to talk about this in any detail today. But again, would be a great topic for a talk sometime, right? Bombs, solar sails, missiles. Do you move it or do you disintegrate it? how far in advance do you have, which are the sizes of objects you really have to worry about, and that sort of thing. All over our solar system, we can see the stars of these kinds of bombardments. On the surface of Mercury, we're just looking at on the surface of the Moon, of course, which is very familiar. And there are even some places on the Earth, although the Earth does a very good job of healing up these stars. Geologists have located at least about 150 places on the Earth where impacts have occurred. A lot of them are in this country because Canada has a really nice hunk of rock around here, the Canadian Shield, or the something shield. What's the Laurentian Shield, which somehow has survived a really long time without being dumped back under the mantle or being repaved in any way. So some fairly old geological scars can survive in this region. The best known of these, and probably really the best one to start with when you're studying impacts, is Meteor crater in Arizona, which is about 1.2 kilometers across. And I'm sure you've all seen it before. This is the Manicouagan feature in Quebec, which is 70 kilometers across. So it's the result of a pretty large impact a rather long time ago. And most of the obvious meteor features are gone from this. But if you get down there and check out the rocks in this vicinity, you can see evidence that they were once part of something that did a lot of melting in a big hurry, shocked material and so forth. Once again, here's another Bill Hartman painting of a collision. I want to tell you the story of how an event like this, an impact event, might occur. An asteroid might hit another asteroid and deflect its orbit, give it some momentum like billiard balls that sends it on some path that eventually, maybe 100,000 or a million years from after this event, will take it to cross the path of the Earth as it goes around and around the solar system. Or it may wander past another planet, which puts a kink in its orbit and changes it a little bit and sends it to intersect the Earth. Or it may get a kink from one planet and a million years later get another kink from another planet and so forth. There are a lot of ways that you can initiate an event of this type. But since the inner solar system is filled with fairly massive planets, it's very likely that these objects will zip by one of those planets and get a little boost or change in their orbits from the planet that will send them scurrying out of our region of the solar system again. So the population of near-Earth objects is a short-lived population from the cosmic dynamics point of view, and it needs to be replenished all the time. Probably there's some process, not fully understood right now, but some process like this, or like perturbation by other planets, that kicks occasionally main belt asteroids from wherever they live into the region of the Earth. Well, everything is fine until our object starts to encounter the Earth's atmosphere, typically at a velocity that is at least Earth escape velocity, 11 kilometers per second, or above, more typically 30, 40 kilometers per second. The asteroid's on its orbit and the Earth's on its orbit, and they generally have different speeds around the sun. So a few seconds before impact, this is the site that you might see, and just at about a minute after impact, you'll see that material has been thrown up from the surface by very large energy of this object. We're talking about maybe sort of multi-hundred meter or kilometer sized object here. And you can see that the material can get thrown pretty far. You can see this on the Moon too, with the rays spreading out from lunar craters like Tycho craters. It can get thrown pretty far, and there's an awful lot of energy in here to excavate a pretty big piece of ground or a pretty big piece of ocean. The interesting thing is that if you put enough material in in the air, especially if you hit an ocean and you put lots and lots of water into the atmosphere, you may make a lot of clouds. If you have solid material kicked up, it makes lots of tiny dust particles, which are excellent places to start new water droplets, and clouds form. If you keep a lot of water up, well, you might form clouds out of the water. David?
Just that the reason why kick-up is so bad is you found on what's called anhydride stations, you may have a lot of sulfur. So you end up with sulfur dioxide, which then ends up with sulfuric acid in the atmosphere, which is what Venus has.
A little sulfuric acid in the atmosphere for a while, or a lot?
Or a lot.
A lot.
There's a couple of papers at Houston this year.
Interesting. Well, here's another effect. This stuff that gets kicked up could be red hot, and we could send it across half the planet with a suitably large impact, and so it spreads all over the place on several continents and starts forest fires everywhere simultaneously. And that puts a lot of soot into the atmosphere, which again can catalyze the formation of clouds. Dale?
Yeah, having to do with what you were saying, the effect you're talking about actually was somewhat delayed. The sulfur dioxide acid rain was going to kill a lot of the plant life, and those forests, which are now dead and drying out, then cause massive forest fires. And there is layers of charcoal that can be found in the geological record, very, very close to the impact event.
The impact event of 65 million years ago, which is hypothetical, but which is becoming more and more convincing as time goes on, was enough to trigger the extinction of a whole lot of animal and plant species through some kind of global effect. And you've all heard about that, dinosaur killers and so forth. Basically what the astronomers are worried about, what the AIAA was worried about, is that this could happen again. It doesn't happen very often, but it could happen any year to us. And once again, the reminder is what's happening in Jupiter next July. This is a picture of my office. I work on the 14th floor right here at Fermi Lab, and this has, as I said, nothing to do with near-Earth objects. But
Are you waving?
yes, that's me waving out. But I'm about to show up a lot of charts and talk about the sizes of objects. So if you know that this is a 16-story building here, and it's pretty much most of a mile from the end of the neutrino line to the headquarters building, the high rise. And then it makes sense that you have some real grasp of what 1 kilometer radius means. The Fermi Lab ring is 1 kilometer in radius. So if I'm talking about a 100-meter object, it's something that goes a tenth of the way into the thing. If I'm talking about a 1 kilometer object, it's one that spans this big. That gives you a mental grasp of such things. Well, here is the best prediction known, and he has large uncertainties, and we probably do better science in refining the uncertainties. Best prediction known for how many asteroids there are of any size in the vicinity that actually cross the orbit of the Earth occasionally. And if you look at things that are larger than 2 kilometers, there's probably not very many of them. There's about 400. Okay. If you look at 1 kilometer, as I said, there's about 2,000. It says 2,100 on this chart. Smaller objects, down in the 10 times smaller in the 100-meter range. Well, there's actually probably hundreds of thousands of them. 320,000, according to this estimate. And 10-meter objects, there's 150 million of them. In fact, 10-meter objects fall all the time on the Earth. And mostly we don't notice them because mostly they burn up. But a 60-meter object, probably more or less, fell on the Earth in 1908 in Tunguska, Siberia, and did this to the vegetation, and would have done an awful lot of damage if you're in the city there. It flattened, it flattened trees and caused big shockwave damage for tens of kilometers around. We don't know that anyone was hurt in this accident because well, there aren't that many people living in Siberia even now. But it's an object which didn't make a hole, strictly speaking. It just sort of disappeared about the time that it was low in the atmosphere. The favorite explanation, but much disputed among experts, is that this was probably a stony object, a rock, if you like, that got hotter and hotter as it came down, and the heat was, although it was intact most of the way down, the heat was enough to vaporize it explosively when it got almost all the way down and produced that shockwave. Here's an example of stuff that Dale and Dave were talking about 65 million years ago. No PBS watcher can be ignorant of this, and I presume the same is true for the CDC. The Alvarez's proposed that a layer of strange stuff found on the boundary between the Cretaceous and the Tertiary period in the age of the dinosaurs had a little more iridium in it and a little funny isotopic balance than you could really account for by its being of terrestrial origin, and probably was triggered by this stuff sprinkled down from the debris left by an impact of a large object. Again, the story is probably pretty familiar to you. Let's look at it. This is a grim slide. They get grimmer about just what sort of terrible things you can expect to happen. The bottom axis is megatons of TNT equivalent energy. Starting at, here's 1 megaton and here's 1,000,000 megatons. This axis is how often does such an event happen? We get probably lots of small 20 kiloton Hiroshima-sized events. In fact, they expect that we get these about annually. And recent data that's been declassified from U.S. Department of Defense, Department of Energy missile watching satellites actually confirms this. We actually, over some ocean or usually in orbit, Antarctica or the Arctic or places where nobody's looking, we actually get a big blast of meteoric energy once a year, every couple of years, something like that. So this is kind of surprising, but these explosions usually happen pretty high up in the atmosphere and they don't have much effect on the surface because the objects are very small. The Tunguska object is expected not to happen real often, somewhere between once a century and once a millennium. This is, as I said, about a 60-meter rock. The 1,000-year event probably like equivalent to a 50 megaton explosion. And somewhere in here, it's a wide range because it's hard to get a lot of scientists to agree just where the global catastrophe happens, just how much energy it takes. There are probably some wonderful optimists who think that it takes 10 million megatons to wipe out civilization. There are pessimists that think it only takes less than 100,000 megatons to wipe out civilization. And it would be fun to be in on those arguments, but the bottom line is somewhere up here, somewhere between every 100,000 years and every 10 million years, we're likely to get about one rock dropped on us. It's bad enough to change the weather for a while and make crops fail and make it hard to find food. If that happens, and we're not prepared for it or dug in with shelters or our cans or something, then billions of people will die. Yes, and this is the wonderful, even grimmer slide. Expected fatalities in events. Okay, this is a real probabilistic thing. I mean, if a Tunguska thing happens and it lands on Tunguska, it doesn't really kill anybody, right? But if it happens somewhere on the Earth, on the average, a Tunguska-sized event will probably kill a few hundred people. You know, if it lands on a town, it might kill thousands. If it lands in a big, wide desert area like Tunguska, it'll kill nobody. And you know, but in this range, we expect. Yes, my battery is dying. We expect. You know, we can expect that this sort of accident will, on the average, whatever that means, lead to hundreds or 1,000-fold fatalities. As impact get bigger and bigger, there's a higher and higher probability that they'll kill a lot of people. And if the object is big enough, this is the megaton scale, and it's also listed as diameter of object here, and this of course makes a certain assumption about what speed the thing is coming in at, 30, 40 kilometers per second probably. And somewhere in this region, somewhere if an object is bigger than a couple hundred meters, maybe the size of the Fermilab ring, like 1 kilometer or 2 kilometers, or bigger, somewhere in this region, depending on the disagreements of different scientists, will kill hundreds of millions or billions of people. World population is up here, so they don't even bother to extend the graph much beyond this. In other words, there's a probability, and it doesn't happen very often, like maybe once in a million years, once in 100,000 years, that some event will kill everybody, or at least say kill billion people. They consider that an event that kills a billion people is probably big enough to worry about. And so the Morrison report concerned itself with civilization killers and said that it's not really so hard. We don't really have to be quite so worried about city killers or county killers.
Unless you're in the city.
Unless you're in the city, and unless you're in the city, that's at ground zero. Or unless some important subcontractor on your project is in that city, I guess. If your boss is in there, headquarters is there, that's not so bad. Well, this is another source of disagreement. The argument goes that if this happens every 100,000 years, and it kills a billion people, happens every 10 to the 5th years and kills 10 to the 9th people, then that's 10 to the 4th people per year who on the average get killed, right? People don't get killed pretty much at once, but on the average, we're killing 10,000 people a year in this kind of accident. If it happens once in a million years, then it's only 1,000 people per year. But even very conservative estimates suggest that we're making a bet here. If we do nothing about this problem, we're making a bet that really is essentially equivalent to hundreds of lives per year. Now, the argument of the asteroid astronomers is that we spend a certain amount of resources preventing 100 deaths a year. Like, we spend some money on airline safety. Seatbelts. We spend money on seatbelts. We spend money on cancer research. Okay? And we do really save lives through those efforts, through putting some of society's resources towards those things. And we have insurance companies, and we take out insurance policies against catastrophes that cause these levels of fatalities. So probably it is sensible to expend some resources that are equivalent to other resources that we spend saving 100 lives a year or 1,000 lives a year, right? And what can we do about this? Well, the first thing we can do, and it's real, this is obviously what's needed, is to catalog all of the rocks in the solar system that have a chance of hitting the Earth and are big enough to cause a very large number of fatalities. Well, how do you find those things? You'd have to hire some asteroid astronomers. And suddenly there would be more work for them. I find this, I find this a self-serving argument, but it's also kind of plausible to me anyway. And since I am very interested in getting more asteroid astronomy done because I think it's interesting, and even more interested because I think that finding these objects will inevitably find the objects which are easiest to get to and easiest to mine and the most abundant sources of possible raw materials for space industry. For all those reasons, I think this might be worth doing, or at least I think it might be worth expanding the world's present effort in this direction. There are 3 groups in the United States doing this, and 1 group in Australia. I think 1 group in Australia lost its funding last year. All right, or as David Morrison puts it, the total number of people working on finding near-Earth asteroids and cataloging them, and discovering new ones, and figuring out what their orbits are, is about the same size as, or it's smaller than, the crew at your local McDonald's. So it seems to me that this is there's real merit in setting up a system like this. They propose that that for a number like about $10 million a year over about 20 years, we could build a system of telescopes and operate them, which maybe, say, 10 telescopes scattered around the world, working on locating near-Earth asteroids using something like the Space Watch technology. And probably, in a period like 20 years, find all 2,000, 2,100, or whatever they are, objects which are big enough to detect easily and big enough to cause a serious threat. Objects, this is the great thing about this report, objects which are small enough to be difficult to detect are considered to be so small that they don't offer a big, dangerous threat to civilization. Now, if you're worried about that, you know, such a search will inevitably find smaller objects, and you could make bigger telescopes or more telescopes, or go to work, get better technology, and try to find even smaller objects. And in fact, the weapons guys are in favor of this. They would like to catalog even unthreatening even threatening objects that are dangerous to people on Earth. You know, if they live in a city that it hits or whatever. Well, instead of looking for a couple thousand things, you're looking for hundreds of thousands of things then, and that would be a big, difficult technology program, which is just the sort of thing they like to develop. And they're looking for work. I mean, even more than asteroid astronomers. The weapons labs are closing down, and the academic astronomers are kind of unhappy or they're suspicious of the weapons folks because the weapons folks need more missions for their laboratories. There's a whole controversy over whether it's appropriate to do asteroid deflection at all. Carl Sagan and Steve Ostro wrote a letter to Nature recently that strongly recommended that no one should develop asteroid deflection, asteroid moving technology, because it was too dangerous for humans to have this. And the probability that sometime in the next million years, everyone will get splashed by an asteroid is probably lower, in their opinion, than the probability that sometime in the next few hundred years, someone will misuse this technology for evil purposes. But I'm not really here to discuss all that. I guess we can take it around in the question period, or at the banquet, right? But that's all I got to say pretty much. It might be wise to invest a bit of resources so that our homes don't wind up looking like this. And it's certainly wise, in my opinion, to think about asteroidal objects in the long term as a springboard for the future of space civilization, which is going to have eventually economic importance to all civilizations. Thanks very much.
Yeah, if you took the amount of money that OSHA was going to force the airlines to spend by putting in safety belts in aircraft, bird life safe, $4,100 million bird life safe,
Okay.
children, times 10,000 lives, that's pretty significant.
Would we save a lot of money if we took safety belts out of aircraft? You know, the whole business of risk and safety and who's, how much should you spend to save how many lives, how do you measure how many lives you save, is just a big can of worms.
matter of fact, there's legislation in Congress this year that forces EPA to basically value engineering on their legislation. The cost per life saved, and to cancel those regulations which are shown to be cost ineffective after 3 years.
Do you think this is a good idea?
Oh, yes.
It depends on whether you use that to prioritize. Pick the ones that cost the least, do them first, and work your way through the list.
Well, there are emotional issues involved here, which you don't necessarily come out quite numerically prioritizing these kind of decisions. And what the heck, these astronomy guys are now treading on dangerous ground and getting into